See, when primary aliphatic amines are treated with sodium nitrite and hydrogen halide, we get nitrous acid. Okay. See, this nitrous acid is prepared in situ. That means internally. I mean, as and when required, because it is unstable. Okay. With sodium nitrite and hydrogen halide, primary amines form diazonium salts. So this process is, of course, diazotization. Okay. We get alkyl diazonium salt. Unlike the aryl diazonium salt, this alkyl diazonium salt is unstable. Okay. Of course, along with this, we get sodium halide and water. But the unstable alkyl diazonium salt loses nitrogen and forms alkyl carbocation. Okay. So this alkyl carbocation may react with water to form an alcohol, or it may react with halide to form an alkyl halide, or it may lose a proton to form alkene. Okay. So these are the three possibilities available for the alkyl group, whatever is formed here. Okay. Along with the alcohols, we get alkenes, even alkyl halides. Okay. So this is how alcohols can be prepared from the primary amines. Next. Now let us go for the properties. First of all, the physical properties. Coming to boiling point. See, the boiling point of alcohols are much greater than their isomeric ethers. The reason is alcohols have got intermolecular hydrogen bonds. Let me show you. Yes. This is how intermolecular hydrogen bonds are formed in alcohols. As a result, to break from association, you require lot of thermal energy. So, the boiling point of alcohols are much greater than their isomeric ethers. Now, within this, we have some other interesting points. As usual, see the boiling point increases as the molar mass increases, because as the molar mass increases, van der Waals attraction between the molecules also increase. Now coming to the isomers. Among isomeric alcohols, boiling point decreases as the branching increases. Because with increase in branching, surface area decreases. We know this. Okay. Now, coming to solubility. See, alcohols are highly soluble in water. Again, because they can form hydrogen bonds with water molecules. Let me show you. This is alcohol and this is water molecule. Again an alcohol, again a water molecule. So this way, hydrogen bonds are formed between the alcohol and water molecules. Even in this also, I have some interesting points. If you observe the alcohol, alkyl group is hydrophobic, whereas this group is hydrophilic. Okay, depending on this, we can say that the solubility of N alcohols, normal alcohols, decreases as the size of alkyl group increases, because these alkyl groups are hydrophobic. You can say non-polar. So are hydrophobic. Now coming to isomeric alcohols. Among the isomeric alcohols, solubility increases as the branching increases. Again, because here the surface area of the hydrocarbon part decreases. Now, because this hydrocarbon part is hydrophobic, as the surface area of the hydrocarbon part decreases, solubility increases. Okay. Coming to chemical properties. The first one is Fischer esterification. Nothing but ester formation from the acid and alcohol. In the presence of acid catalyst, a water molecule is eliminated and we'll get ester. See, the forward reaction is esterification, nothing but the formation of ester. Whereas the backward reaction is what we have already seen, that is ester hydrolysis. Okay. Examples. See, when acetic acid is treated with ethyl alcohol, look at this. Here the bond between oxygen and hydrogen of alcohol undergoes cleavage. So that is an important point. And we'll get ethyl acetate plus water. To know the mechanism of where the bond is undergoing cleavage, we can take labeled isotopes. Like, for example, when benzoic acid is treated with methyl alcohol, let me take O18. Now, even here also we can show that the bond that undergoes cleavage is between the oxygen and hydrogen of alcohols. If that happens, then only we get O18 here in the ester. Okay. Now let us see the mechanism. Acid with H3O plus. See in this, water molecule is eliminated here and we'll get RC double bond O, a pair, then this H, and of course this. Now the alcohol comes into picture. Look at this. Towards the positive charge. RC, then this is OH, one more OH, then this R dash OH. Okay, a positive charge. Now, as usual, this H plus is last and the bond is given to the positive charge. See here. RCOH, then this one is OR dash, then again this. Now, see, a carbon having two hydroxyl groups is highly unstable. One, the second one. Now, as and when this one comes here, of course, I can show directly like this one comes, but let's see. One extra step for clarity's sake. Now, RC double bond O, then a positive charge, a H, O, R dash. Okay. Now, we can take out that H plus using a water molecule. Abstracts the proton and this goes towards the positive charge. Finally, we get this ester part. Okay, minus H3O plus, the thing what we have used in the first case, because acid is the catalyst employed here. See, in this case, reactivity order can be given in terms of alcohols and in terms of acids. In both the cases, you know, the reactivity is inversely proportional to steric crowding or steric hindrance at or around the carboxylic, the alkyl group of the carboxylic compound or the alkyl group of alcohol. More steric hindrance, less is a reactivity. Now, in case of alcohols, it can be given as the basic alcohol, methanol, with almost zero hindrance, is most reactive. Then comes ethanol. Next, it's bit more crowded, isopropyl alcohol or propan-2-ol, you can say. Then look at this, much more crowded, a tertiary butyl alcohol. Now, in case of acids, if we see, even in this case also, basic or the parent acid, formic acid, will have the maximum reactivity. Because of this hydrogen, which doesn't produce any steric hindrance. Then this acetic acid, take isoburic acid. Finally, this. Okay. Let us take some more reactions involving the same OH bond cleavage. I mean, the bond between oxygen and hydrogen undergoes cleavage. Look at this. ROH, then R dash COCl with acid halide using pyridine. See, pyridine is generally used to remove the byproduct, that is HCl. Let us just remove HCl. Look at the cleavage. OH bond has undergone cleavage. R dash, C double bond O, then O, R, plus, of course, HCl. Then, see, when alcohols are treated with acid anhydrides, the same thing. Pyridine, but here it is to remove acid. Look at this. H along with this. Okay. And the bond that has undergone cleavage is this. We get R dash, C double bond O, O, then R. R dash C double bond O OH. Acid is a byproduct. Next, with the Grignard reagents, ROH plus R dash MgX. See, because this hydrogen is acidic, it is eliminated. I mean, it goes off along with the R dash. And we'll get R dash H. Okay. Alkane is formed. Along with that, of course, MgX, then OR. I mean, alkoxy magnesium halide is what we get as a byproduct. See, when alcohol is treated with dimethyl sulfate in the presence of a base, take 2 molecules of alcohol, then we'll be getting 2 molecules of ether along with this sulfuric acid. Look at what has happened. 2 hydrogens with this SO4. I mean, again, the bond that undergoes cleavage is this. You got ether, the preparation method of ether, property of alcohol. Let us now go for a very, very important named reaction. Haloform reaction. See, I've taken a methyl ketone, isn't it? So this is methyl ketone. Now, when this is treated with halogen, we get R C double bond O CX3. Okay. Of course, by the elimination of HX. Now, when a base is used, it is actually with halogen in the presence of alkali. We get R C double bond O minus, along with that a haloform. Mechanism is very interesting. Let us take the methyl ketone this way for convenience, making use of OH minus. A hydrogen is abstracted. Then we get R C double bond O CH2 minus with the halogen. We'll get R C double bond O CH2, then this X. Now this is how we can actually repeat the same steps for 2 more times. Okay, of course we get R C double bond O CX3 because even these two hydrogens are substituted. Okay. Now this RC double bond O CX3 with OH minus. See, it attacks this. Of course, this goes off, but let me give you this way. Now we get RCO minus this OH and then this CX3. Now, as and when this comes back, this will go off. So we get R C double bond O OH. Of course, the CX3 minus. Okay. And now the CX3 minus abstracts a proton to finally give R C double bond O minus, the carboxylate anion and the halo form. Okay. So this is halo form reaction. A very important one.